Hi again. This is video 2 for chapter 6 on multiple regression. And what we're going to talk about next are the assumptions that we need in order to make least squares a good estimator, the estimators that we've been using. So the least squares assumptions in multiple regression. Least squares assumptions in multiple regression. Okay, assumption 1, the first 3 are exactly the same as they were for the 2-variable model. We're just generalizing, so we have more than one x. We have kx's on the right-hand side, and we'll just slightly generalize. And then in the multiple variable context, we're going to have to add a 4th assumption that we didn't have before. So these first 3 shouldn't be anything new. They're just generalizations. So this is the one that the conditional distribution of the error term of ui given x1i up to xki has mean 0. That is, the expected value of the error term ui given x1 through xk has to be 0. And this is the same as before. The main way that this will be violated is if the error term is correlated with any one of the x's. That's going to create troubles. And in general, what will happen if the error terms are correlated with the x's is we'll get bias in the model. So again, this just extends the assumption we had before. Assumption 2 is simply another extension for the multivariate context. It's that this one says that yi x1i up to xki, that set, that's a particular observation for the ith person for I equals 1, 2, up to n are IID, independently and identically distributed. And again, mainly what we're saying here is this holds if we have random sampling. So when this tends to be violated is if somehow we don't have a random sample. We don't look at every district in California for test scores, and somehow we oversample the districts that have high income or oversample the districts that have high immigrants, something like that. That's going to give us a biased estimate relative to the population. So we have to be careful that our estimates are random. The third assumption, let me just erase here and give myself some room. Again, there's nothing new here. This has to do with the error term, just like it did in the 2-variable case. Assumption 3 is that large outliers are unlikely. And the book gets way more specific about exactly what that means in terms of the fourth moment. The fourth moments have to be finite for all the variables, but we're not going to worry too much about that. The upshot is you can't have, this is about the distribution of the error term, the UI. It can't have fat tails out there. There can't be high probability that we get really, really big numbers away from the mean. And again, remember the reason for that is that upsets our convergence properties. The law of large numbers might not hold, and we might not have consistency of our estimators in those cases. Now, the fourth assumption is the new one. It wasn't an issue with just 2 variables, but it is, and we've got more. And this one says that there's no perfect multicollinearity. I haven't told you what multicollinearity is. I will in a second. But there's no perfect multicollinearity. What that means is two of the variables can't be perfectly correlated. I can't write one variable as a perfect linear combination of another. For instance, if I can write x2i is a0 plus a1 x3i, no error or anything, that's an exact, maybe x2i is 4 minus 3.5 times x3i. If there's an exact relationship among variables like this, then if I have both the variables in the model, then you can't even estimate it. Your estimators will fail. What will happen technically is you'll end up with a divide by zero problem. And so, for instance, if I had, this is a trivial example where you'd have a perfect relationship. Suppose I have one variable in feet, and then I just convert that to inches, and I put that in the model as well. Then one variable would just be 12 times the other. There's a perfect relationship, and the estimators would fail. You can't estimate at all. And so there can't be any sort of exact relationship among the variables. Now the solution to this is pretty simple. You just drop one of them. Throw out feet or throw out inches. It doesn't really make any difference, but you need to throw out one of the variables. Then you don't have perfect multicollinearity anymore, and you're fine. So here you could either throw out x2 or x3. Basically, these are the same information. These are perfectly correlated. See, the problem with perfect multicollinearity is in a multiple regression framework, here's what OLS essentially does. You have yi is beta 0 plus beta 1 x1i plus beta 2 x2i plus beta k x ki plus ui. So that's the multiple regression model. Now, how does it know what numbers to give this? Well, intuitively, what OLS is doing behind all the math is it says, let me find a time when x1 moves all by itself and the other things don't move at all. So let me find a movement in x. So this goes up by 1, say, and then it says, how much does y go up? Well, y goes up by 2. Oh, this coefficient must be 2. Then it finds another time in the data. Remember, we've got n observations. That's one of them, where x1 moves and the other things sort of don't move in a way that can be traced to y. You say, oh, this time when x went up by 2, y went up by 5. Oh, the coefficient's 2.5. And then it keeps doing that, and then it sort of averages all those relationships. One was 2, one was 2.5, one's this, one's that. And so what it does is it looks for unique movements in one of the variables, so that it can look at what happens to y, and then it can figure out what this coefficient is. If x is moving, all else equal, and y doesn't move at all, then it gives it a 0. When you have perfect multicollinearity, there's perfect correlation. Say that x1 and x2 are perfectly collinear. Then whenever this goes up by a certain amount, this goes up by a certain amount. Whenever this goes down, this goes down. If they're positively correlated. There's no unique movement in either variable. So it can never figure out whether it sees x1 move and x2 always moves with it. So it can't figure out whether it should assign the effect to beta 1 or beta 2. And when it can't figure that out, it just falls apart. Now, later on, we're going to have something called imperfect multicollinearity, and what's going to happen is you're going to get really big standard errors because it's not going to know which of the two things to assign it to. But in this case, it literally has no way of figuring out whether beta 1 should get the effect or beta 2 should get the effect, and the whole thing just collapses. And again, the solution is just to throw one of those variables out. Okay. So those are the new assumptions. Again, the only new one there is perfect multicollinearity, and we're going to come back to this collinearity idea, multicollinearity idea in a minute, and look at less than perfect, what's called imperfect multicollinearity. That was only for perfect multicollinearity. Okay? Imperfect, you can still estimate with imperfect multicollinearity, but it creates other problems we'll talk about. Okay. The distribution of the OLS estimators in multiple regression. There's nothing much new here relative to The two-variable case, it just basically extends what we've already done. And so this can be done rather quickly. This is section 6.6. So the question of what are the distributions of beta naught hat up to beta k hat? How are those things distributed? Remember, these are random variables because each time we draw a sample, we'll get different betas. And what we hope is that on average, if we repeatedly sample from a population, we'll get the right value, or if we go to infinity, so we sample the whole population, we'll get the right values. So the first thing is just like before, under the assumptions, they're unbiased estimators, and they're consistent if the four assumptions hold. So that's good. If we repeatedly experiment, repeatedly take a sample of, say, 100 from a population, calculate the betas, well, let's say 200, so we have the large sample. Remember, we said we need more than 100. Let's do 200, say, and we draw a sample of 200, estimate these, draw another sample of 200, estimate these, draw another sample of 200, estimate these. On average, we'll get exactly the right numbers, or if we let n go to infinity. And so these things are right on average. Secondly, the joint sampling distributions of beta naught hat, beta 1 hat, up to beta k hat are well approximated by a normal with mean beta I and variance sigma squared beta hat I. We're not going to actually write the formulas for these sigma squareds, just like we didn't write the formulas for the beta hats. They're too complicated unless we use matrix algebra. But again, this is what comes out of the printout. You get an estimate of this thing and an estimate of this thing. But so just like before, they're distributed normally with this mean. They're unbiased and consistent, and that's the variance. There are formulas for those variances that we could write down, but again, they're very, very complicated, so we won't do it. But the point is that these things are normally distributed, so hypothesis testing isn't going to be all that difficult because we can rely upon the normal approximation. And that's just another way of saying that the third thing here is the central limit theorem applies, just like it applied in the two-variable case. And so the beta hats converge to, that means converge, to a normal beta I, sigma beta hat I, sigma squared, as the number of observations goes to infinity. And that's no matter what the initial distribution of the errors are. It doesn't make any difference what kinds of distributions we start with. These beta hats are essentially weighted averages, and so we can use the central limit theorem to work out that these things are in fact normal. And so again, that's going to be very helpful when we do hypothesis testing in the next chapter. So the beta hats are normally distributed, and we'll come back to that when we do hypothesis testing. Okay, let's go back to this notion of multicollinearity. So we've already talked about perfect multicollinearity something like x3i is a0 plus a1 x2i, for example. I mean, that's not the only, it's not just x2 and x3. You could have more variables. It could be plus a2. You could have plus a2 x4i, and you could have all sorts of, as long as it's a perfect relationship, as long as there's no error there, then you'll have perfect multicollinear. So this was perfect. There's perfect correlation between these variables. You can't tell them apart. The regression model can't tell them apart, and that's why the regression fails. It looks like the same variable to the model because they move identically. They're perfectly correlated. If you have imperfect correlation, then it's something like x3i equals a naught plus a1 x2i plus some error, ei. This is some error. So now if the variance's error is really big, these things aren't going to be very correlated because a lot of the movement in x3i will be due to ei. So in this case, they're imperfectly correlated. Or we say we have imperfect multicollinearity. And so, I mean, it's not always, the reason why we don't want to just talk about correlation is, again, I could have more than one variable. I could have plus a2 x4i plus ei. Then the idea of being correlated with it doesn't really make the, but that's what we mean by, this is imperfect multicollinearity. The variables are correlated, they move together, but they don't move perfectly together. So whenever x4 moves, x3 moves, but sometimes x3 moves when x4 is constant, and sometimes x3 moves when x2 is constant because of the ei. And so there's movements in x3 that are unrelated to these two things, and so they're not perfectly related. They're not perfectly collinear. Okay, so there's two types of collinearity. There's perfect, where there's an exact relationship. Then there's imperfect, where things are highly correlated. They move together, but they don't move perfectly together. As an example of perfect multicollinearity, let's talk about the dummy variable trap. There's lots of ways that you can run into this problem. For instance, suppose that you put into a regression, you put the percentage of English speakers, aside from the dummy variable trap. Suppose that I have a model yi is beta naught plus beta 1 x1i plus beta 2 x2i plus an error term ui. And this is the percentage of English speakers, and this is the percentage of non-English speakers. Well, the percent English speaking plus the percent non-English speaking has to equal 100%. So there's an exact relationship among these variables. So if I tried to put both of these into my model, both of these two percentages, I'm going to, the model's going to fail. I'm not going to be able to estimate my coefficients. And you might think, well, how can you get an effect, you know, suppose I want to know about this beta 2, the effect of non-English speakers on yi. You can use this relationship. You can, what you would have to do in this case is drop one of the variables. Then you could use beta 1 estimate to figure out what the effect would be for the non-English speaking. See, let me come back to the dummy variable trap in a second. Let me just show you how this works. So we have this model that says yi is beta naught plus beta 1 times the percent English speaking plus UI. And we know that the percent English speaking equals 100 minus the percent non-English speaking. Okay? So we can't put both of these variables in there because then we have perfect multicollinearity. There's no error in here. They're perfectly related. You got more English, you've got less non-English speaking. I mean, that's just, they're perfectly correlated. Well, I could estimate and get beta naught hat and beta 1 hat. And beta 1 hat's the effect of a change in the percent English speaking on yi. But what if I want the other? Well, you can just sub in. yi is beta 0 plus beta 1 times 100 minus percent non-English speaking plus ui. So this would be yi is beta naught plus 100 beta 1 minus beta 1 times the percent non-English speaking plus ui. And so the effect of the non-English speaking is just minus the effect of the English speaking on yi, which you'd expect, because if one goes up, the other goes down. So you're going to get exactly offsetting effects when you estimate it. But you don't have to have both variables in the model to know what this. Now if I increase the percentage of non-English speaking by 1, which is the same as reducing this by 1, this will go down by beta 1, or if we do it the other way, this goes up by beta 1. It would go down by beta 1 too, because if this goes up, this goes down. And so it's the same model, it's the same thing. It's just that you can only put one in them at a time, but that doesn't mean you can't understand what happens to both components of it. I hope that makes sense. Hope so. Okay, let's go back to the dummy variable trap. It's going to be much the same thing. And this is an example of multicollinearity. So let's divide our school sample into 3 parts. So let's suppose we have information on their location. We want rural, urban, and suburban. I meant sub first, suburban and urban. And I'm going to define 3 variables. I equals, so for the ith district, this will be equal to 1 if it's an urban district and 0 otherwise. I'm going to define a second variable, suburb, for district I, will be 1 if suburban, 0 otherwise. And you can imagine the third variable will be rural. I will be 1 if rural, 0 otherwise. And every district will fit into one of these categories, but it can't be more than one. So these are unique categories, and we're going to set we're going to assign one of these categories to every district. Now, let me show you something. We're going to number the districts. 1, 2, 3, 4, 5, down to 420. And we have a bunch of different variables. So you can imagine this is an Excel spreadsheet. So these are cells down to the 420th. In column A, we're going to put score for district I. These are the I's from 1 to 420. We're going to put class size, STR, for each of them. then we're going to have a constant term. And then we might have other variables like percent immigrants and all those things. I just want our three variables, suburban, urban, and rural. So we've got these categories. So each district is going to have some data on score and STR, score, STR, score, STR. These are numbers in your spreadsheet down to the 420. I'm not too worried about that. Now this constant term, what am I thinking of there? You can think of the regression model as, I'm going to write over here and then erase it, as yi is beta 0 times 1 plus beta 1 times x1i plus ui, and I could add more x's. But the x here is always 1. And so I'm going to write those 1s. There's actually an x here, x0i. But x0i is always 1. And so the constant is 1, 1, 1, 1, 1, down to 1. That's this variable. That's the constant. It's a constant 1. You literally, inside the, when it runs the regression, if you were to run this regression, it would literally run yi on a 1 and x1i, a vector of 1s and a vector of x's and a vector of y's. So these are all 1s. That's the constant. That's the thing attached to beta 0. Now each one of these schools, let's say the first one is rural. Second one's suburban. Third one's suburban. Oops, this is 0. The fourth one is urban, another rural. And this last district down here is, I don't care, it doesn't make any difference, whatever it is. So this is yi. This column here is yi. This is x1i. I should have put the constant first. This is x0i, that's that constant. This is x2i, x3i, and x4i. Down to here. I guess I probably should have put the labels down here. I wanted to put them up on top, but I don't think you can see that. I think I'm already might be above the top of the. I hope you can see the very top here. This first column here is score, just in case you can't see. This is STR, constant, suburban, urban, and rural. I shouldn't have that in the middle of my spreadsheet, either one of these. Those are just labels that I'd like to put up on top, but I ran out of room. What I want you to notice, though, is that if I add up this plus this plus this, what do I get? I get 1. If I add up this plus this plus this, what do I get? I get 1. If I add up this plus this plus this, what do I get? 1. That plus that plus that, 1. So x0i, the constant, is equal to x2i plus x, is that right? 3i plus x4i. There's a perfect relationship between these three variables and the constant. So if I were to try to run a regression, suppose I try to run a regression of score for district I is beta 0 times 1 plus beta 1 times STRI plus beta 2 times URB I plus beta 3 sub URB I plus beta 4 rural I plus ui. What's the problem? The problem is that urb I, x2, plus suburban I, plus rural I, will always equal 1, the coefficient, the variable here. So there's a perfect, we have perfect multicollinearity because those three variables always sum to the constant. And that's called the dummy variable trap. If you have three categories and you define a dummy variable for each category, you can't include three dummies. That were supposed to be dummies. What you're going to have to do is pick one of them, and it doesn't matter which one it is, and throw it out of your model. So just drop one of these variables from the model. Then, if you don't have that in there, that plus that doesn't equal 1, and you've lost your multicollinearity. And so, whenever you create these dummy variables, and I'll give you a few more examples in a moment, if there are G categories, then you can only include G minus 1 dummy variables, 0, 1 variables. Otherwise, you'll have the dummy variable trap. You'll have perfect multicollinearity. What happens is that the one you exclude gets absorbed into the constant, and that becomes your baseline. Let's do a simpler example to illustrate the dummy variable trap again and how you work with these models. So let's have two categories, male and female. So those are our two categories. And so let's have the variable mi equal 1 or 0 if male, 0 otherwise. And we're going to put everyone into one of these two categories. If you want to generalize it, you can add a third category if you want. It just makes the example harder. If female and 0 otherwise. And there's a perfect relation because mi plus fi will always equal 1. Because you can only be one of the two. So if this is 0, that's 1. If that's 0, that's 1. And so those two things are perfectly related. And so I can't include both in a model. And so what you do is you just pick one. So let me pick fi as my variable. I can't put both in. If I try to run yi equals beta 0 plus beta 1 fi plus beta 2 mi plus ui, then I'll have perfect multicollinearity. And the reason is because fi plus mi equals 1, the coefficient there, the variable there. And so I can't run that model. So, but what we could do is drop one. So we can run yi equals beta 0 plus beta 1 fi plus ui. What happens now is that male becomes the baseline. And so if you look at this model, when you estimate, the expected value of yi equals beta naught if male. So beta naught's the baseline, and the expected value of yi, because if it's male, this is 0, equals beta 0 plus beta 1 if female. And so when I do this, beta 0 is going to be the effect for males. It's going to capture the effect for males. And beta 1 is just going to be the incremental effect over beta 0. It's going to be the difference in the two. And so beta 1 would be the way you would test if there's any difference between males and females. Now you might think, okay, well, what if I put mi in there? Wouldn't I get different estimates? And the answer is no. Because what you can do is say yi equals beta 0 plus beta 1 times 1 minus mi, because that's what fi equals, plus ui, right? Fi is 1 minus mi. So yi equals beta 0 plus beta 1 minus beta 1 mi plus ui. So let me call this yi equals, say, gamma naught plus gamma 1 mi plus ui. If I run this regression and I get gamma naught hat and gamma 1 hat, they'll be exactly equal to gamma naught hat will equal beta naught hat plus beta 1 hat. Gamma 1 hat will just be the negative of beta 1 hat. You get exactly the same. When it's male, you get beta 0 because you get this plus this minus this, and when it's female, you get beta 0. So this is gamma 0 hat is now the estimated effect for a female. It's beta 0 plus beta 1 from up here. And this is the effect of a male, and it's just the negative of the effect for a female, because if you have one more male, you have one more, So that's not what I meant to say. But the effect on males here is just exactly the negative of the estimated effect on females. And so gamma 1 that you estimated would literally be minus beta 1 hat. And gamma 0 hat would be beta naught hat plus beta 1 hat. And so it doesn't make any difference which way you do it. You get exactly the same answer. So beta 0, the constant, is the baseline, and it picks up the effect for males. And then the beta 1 gives you the difference between males and females. So this going to be positive or negative. The other way that you can get rid of multicollinearity is by dropping the constant. And so it doesn't make any difference which of the three variables. Here, mi plus fi equals the constant. It doesn't matter which one you drop. So another way you can overcome it would be to say yi equals beta 1 fi plus beta 2 mi plus ui. And you could run that, and there's no problem. Now, how is that related to the first regression? Well, remember that mi is 1 minus fi. So yi is beta 1 fi plus beta 2 times 1 minus fi plus ui. So here you would get that yi equals beta 2 plus beta 1 minus beta 2 fi. So if I were to run the first regression, if I run this regression here, if I run a regression with just females in it, these are the coefficients that I'd get. The beta 2 is the effect for males, like it was in the very first model. And then the difference between them is just the female effect. And so this model is exactly equivalent. Once I've estimated this, I can find these coefficients. It's just beta 2 hat, and this is beta 1 hat minus beta 2 hat. So estimating this is exactly like estimating this. And so which of the variables you exclude doesn't matter. You can, after you've estimated, you can transform to whatever model you prefer. But again, the big lesson here is that if you have two categories, you can only include one of the categories in the model. Or if you want to include both categories, you have to throw out the constant. And that's always going to be true for these dummy variables. So if you had you want it yi is car sales. And you've got 4 different colors: red, white. These are not very good choices. Blue, so far. And orange, I don't know where I came up with orange. Then you could have Ri equals 1 if red, 0 otherwise, Wi, Bi, Oi, 1, 0, 1, 0, 1, 0. All the cars are one of those four things. So this is Wi is if white, Bi is if blue, Oi is if orange, and all the other ones are otherwise. And I want to know about car sales as related to these. Well, there's two different ways I can run the model. I could make, say, red my baseline. So I could say sales are beta 0 plus beta 1 times Wi plus beta 2 times Bi plus beta 3 times Oi plus Ui. So what if the cars, what's the baseline? Red. So for red, the effect will be beta 0. For white, it'll be beta 0 plus beta 1. For blue, it'll be beta 0 plus beta 2. And for orange, it'll be beta 0 plus beta 3. So these are the differences in the car sales. So if you want to know, is there any statistically difference between red and white? That's beta 1. You test whether that was 0. Is there any difference between red and blue? Any difference between red and orange? Well, that's beta 3. So red becomes your baseline. And you can make any of them the baseline. And once I've estimated this model, I can use that 1 equals red plus blue plus white plus orange. I could plug in for any of these and get the effect for red. You can make, just by making, so if these compare white to red, blue to red, orange to red. If I want to, say, compare blue to white, I could just make white the baseline and run the regression again, or I could put this in and figure it out. It's probably easiest just to run the regression again. But anyway, what you can't do is include all of them at once. What you could do is you could throw out the constant. Then you could have plus beta 4 Ri plus Ui. And then you'd want to test, if you wanted to test white and blue, you'd test that beta 1 equals beta 2. If you want to know if blue and orange are the same, you test that beta 2 is beta 3. If you want to know that red and white are the same, you test that beta 1 equals beta 4. We haven't learned to do those kinds of tests yet. That's what's in Chapter 7. And so running it this way, by dropping the constant, you could compare any colors fairly easily just by doing a test. If I want to know, is there any difference in sales between white and red, it's whether beta 1 equals beta 4. Your null in that case would be that beta 1 minus beta 4 equals 0. With your alternative, with beta 1 minus beta 4 does not equal 0. And that's a test whether there's a difference in sales between white and red. And I could do that for any of them. And I could do these same tests no matter what model I run. And so it doesn't make any difference how you do it. But this is a convenient way, just dropping the constant. But you have to drop something, or you'll end up with perfect multicollinearity. Well, hopefully that's clear. So whenever you have perfect multicollinearity, the solution is to drop one of the variables. Now let's start talking about imperfect multicollinearity. That's when several variables are related but not perfectly. So maybe x4i equals minus 2x2i plus 3x6i minus 1/2 3i plus ui. And it's this plus ui that makes it imperfect, because now x4 can move independently of these things. Oh, that's not the regression error, that's some other error, call it ei. So essentially we have something like this in mind. There's a relationship, but it's imperfect. The correlation is less than perfect between the two variables. So here's an example from the book. So we have this model that was score equals beta 0 plus beta 1 times the student-teacher ratio plus beta 2. I think I said this wrong last time. This is the percentage English learners plus UI. So this is the people, I think I said it's not where they're, I think I called this not where English was not the native language. This is English learners is what this stands for. So the notion is if you have more English learners, you'll have lower test scores. So your null is probably that beta 2 is less than 0 here. Now consider adding a variable first generation. So you're the first generation in the US. It's the generation you are in percent first generation to the regression. So now you would have score equals beta naught plus beta 1 str plus beta 2 times the percentage of English learners plus beta 3 times, the book says percent first, plus an error. So you want to run that model. The problem here is that it's probably the case, it's likely that percent English learners and percent first are highly correlated. That is, they're imperfectly collinear. And this will happen a lot in models. What are the consequences? Well, let me make some room. What are the consequences of this? So this is imperfect. The consequences of perfect multicollinearity is you can't even estimate the model. You got to throw one out. Now we've got imperfect multicollinearity. What are the consequences of that? Well, the first is that the estimates are still unbiased and consistent. So it doesn't mean we can't estimate the model, and it doesn't change the bias or the consistency. The problem is, but the standard errors go way up. You get huge standard errors in the presence of imperfect multicollinearity. Here's why. You have yi equals beta 0. I'm just going to write a simple model plus beta 1 x1i plus beta 2 x2i plus beta 3 x3i plus ui. Suppose x2 and x3 are highly correlated. We're still going to get unbiased and consistent and efficient estimates, but the standard errors will be big. And here's why. Remember how I said it figures out what beta 2 and beta 3 should be? What OLS does is it says, okay, I've got these three variables. I'm going to scan through the data, and here's a time when x2 moved, and these two things didn't do much, and y moved. So this went up by 2, this went up by 4. Oh, the coefficient must be 2. It does that for all the times it can find where x2 moves sort of independent of x3 and x1. And there's ways that it can search to do that. And then it takes the average effect as your estimate of beta 2. And so if x1, x2, and x3 are independent, they're what we call orthogonal. When you do experimental design, you make sure that these things move independently so that OLS can figure out the coefficients as precisely as possible. You avoid multicollinearity with a plague. You make them what are called orthogonal, so there's no correlation at all. In any case, when they're highly correlated, what happens is whenever x2 moves, x3 moves. Most of the time, almost always, when x3 moves, x2 moves. So it never finds independent variation. So it sees both x2 and x3 move, and it sees y move, and it says, oh boy, I don't know, should I put that on beta 2? Should I put that on beta 3? I don't know. And it just puts it somewhere, and it says, what this means is I have a lot of uncertainty, and that uncertainty blows up the standard errors. It's not sure whether the movement in y is due to x2 or x3. Occasionally, because they're not perfectly correlated, it can find an x2 that moves by itself, but not very often. And occasionally, it can find an x3 that moves along with that x2 moving and use those to get some idea of what the coefficients are. So it doesn't blow up entirely, but it only has a couple of those observations because they're so highly correlated, they rarely move independently. And because there's only a very few of them, it's very uncertain. And so what happens is the standard errors for beta 2 hat and beta 3 hat will go up a lot. And if you think about a t-statistic, where you have the estimated minus the hypothesized over the standard error, when these standard errors go up a lot, which is what happens, your t-statistic goes down, and you're very unlikely to reject. So typically, what you'll see with multicollinearity is you'll see beta 2 and beta 3 will be statistically insignificant because they have such large standard errors. That doesn't mean they shouldn't be in the model. Next chapter, we'll be able to test whether these two things should be in the model jointly. We'll do a joint test. So we'll ask if beta 2 and beta 3 are simultaneously 0. And if that test is rejected, if we find out, and that'll be an F test, if we find out that beta 2 and beta 3 ought to be in the model, because when we do a joint test, it's highly significant, but individually they're insignificant, that's one way to detect multicollinearity. Another is just to look at the correlation, because you can use the computer to find the correlation between these really easily once your data's in there. But anyway, the problem then is that the standard errors get blown way up. We can be a little more precise in a simple case. Let me just show you some math. If you have an even simpler model, yi is beta 0 plus beta 1 x1i plus beta 2 x2i plus ui. You can show that sigma squared beta hat 1 is 1 over n times 1 over, I won't do this, rho squared. That's the correlation between x1 and x2 squared times sigma squared u over sigma squared x1. So it's possible to show the sample estimate is an estimate of this thing, but this is the variance of beta 1 hat, the variance of the estimator beta 1 hat. And this is the correlation between x1 and x2. As these get highly correlated, what happens? This number gets close to 1 and then we square it. When this gets close to 1, even 1 squared, what happens is this becomes a very small number. So we get 1 over a very small number. That's a big number. So as rho squared of x1 and x2 goes up toward 1, sigma squared beta hat 1 goes up toward infinity. If this was literally 1, that's perfect multicollinearity. You have an infinite variance and things fall apart. That's again an example. We're dividing by 0. You can't divide by 0, but it approaches infinity. That's what I said. You get all sorts of divide by 0 problems when you have perfect multicollinearity. And this is just one of them. That's not the only one. But the point is that as these things get more and more correlated, but it's not perfect, this gets closer to 1, then this thing blows up to a great big number. So how do you solve this? Well, you can't drop one. Remember, with perfect multicollinearity, the solution was just to drop one of the variables. But you can't do that here. Why not? Let me focus back in on here. If I drop one, it goes into the error term. Remember that? This is the true model. If I estimate with just this, then this is my error term. But now I've got an omitted variable problem because this is correlated with this. It's highly correlated. They're imperfectly multicollinear. And it causes this. So both of the conditions for omitted variable bias would be there, and beta 1 would be hugely biased if there was a high degree of correlation between these two. So you can't just drop it and leave it in the error term. That's not going to work. The best solution is to get more data. What this actually is, remember I said that the problem here is that you get very few unique movements in x1 and x2. They're highly correlated, so they tend to move together. And every once in a while they move separately, but mostly they move together. But sometimes, but not very often, they move apart. If I increase my sample size, I'll have more times when they move independently. But it's going to take a huge sample because they're so correlated to get a lot of independent movements. But if there's a way to collect more data, that's the very best solution to multicollinearity. Often you're stuck. You can't drop it. You can't get more data. And you just have to live with the fact that your estimates of beta 1 and beta 2 are going to be imprecise. Like I said, there's a way to test whether jointly they affect yi, whether they should be in the model. We'll learn about that in the next chapter. But you won't be able to identify very precisely the individual effects. Well, that ends chapter 6. Chapter 7 next. Thank you.